All right, hello everyone. Is the sound okay for in the back? All right, great. So we're following Epic, and this is not completely innocent because in fact what we're going to talk about is agnostic spectral rendering using Predict Engine. So just to introduce myself real quick, so I'm Thomas Laberdance, I'm sales director for UVR. I've been working with them for about 3 years now. And before getting into the technical stuff, I just wanted to show you what can be done using Predict Engine well, in general, you'll see. So just to give you a quick overview of what UVR, where UVR comes from. So originally, UVR was created by two researchers coming from some universities in France, and the real idea was to provide a tool that could act as a render engine for designers, but could also act as an optical simulation tool and really bridge the gap between those two worlds. Here, what you have in this scene that you saw also in the video that you just saw is in fact kind of the illustration of the in-between that we have, because we have the optical simulation part with all of the materials that were measured for this particular vehicle, but you also have the environment that was 3D generated and that is completely comes from a 3D artist pipeline. So the idea behind this is that we bridge really the gap between the world of designers and the world of optical engineers, using parameters from the spectral world for polarization. We use material properties. Of course, we're here, so we support AXF, and I'll dive a bit more into it. But what is important to see here is that everything is characterized in order to provide a single source of truth for designers to do beautiful images, to do some realistic images, but you can also do some false colors validation based on spectral measures and based on measurement for the entire environment. And I'm specifying this because we have a suite of products. The main one being, of course, Predict Engine, which is the render engine. It's a spectral renderer, and I'm putting the emphasis on spectral because here we use the spectral information natively within the rendering, which is a big deal for us because there are a lot of problematics for the industry because they need the spectral information to validate the color, and I'll dive back into it afterwards to see why. The other products, Predict Matter, is completely linked to Predict Engine because it's a library of assets that are measured for materials, lighting. So we have the light information from the luminaires in the scene, but also from the environment. We have Predict Lab, that is a physics-based and optical analysis tool, and Predict Sky, that simulates sky based on location, time, environmental factors with the spectral and polarized information contained within the sky. So you see in the top left corner that we have UVR within Unreal, within Unity, within Blender, within Omniverse, and that's a key aspect for us because we don't have our own proprietary 3D platform. This is not the goal. Our goal is to provide like a universal industrial render engine without breaking any of your pipeline. If you have your own application within Unreal or within Omniverse or using pretty much any other 3D platform, we worked really hard, in fact, on an API. We took at least 3 years to really make sure that it was available and could provide the spectral and polarized information using a whole bunch of microservices that you can connect either on-premise or in the cloud, so that you could have all of these services available via the API, so that you can use it in your own platform. And that way you get this great renderings that you saw in the video within pretty much any platform you'd like to use. And I mentioned the measurement pipeline. The idea is that we have supported the material measurements, but we go a bit further than this. We want to characterize basically everything you can have in the scene. We of course have the luminaires information, the spectral information for the inputs, for the displays also we can measure the displays, we can measure the spectral information for an environment to have spectral HDRIs, available so that you have the correct behavior between the lighting and the materials, and the possibility to characterize sensor response so that you can correctly see how the camera will behave. And the validation side of things is that we do all of this, we will do all of those characterizations to achieve what we call ISO-photography. We mentioned yesterday, Porsche mentioned it yesterday, that in fact we have a bias from the vision side of things. So in order to validate from one individual to another, it's really complicated. And here, for validation, but also other use cases like sensor simulation, we can in fact simulate the behavior of the sensor to validate the approach in order to compare the images. So you have, of course, a picture on the right and the render from Predict Engine on the left, and you can compare the spectrums of the two results between the simulation and the measurements. So of course you can do delta E because delta E is the standard for color comparison, but you can also dive a bit more into it to see where the error might come from when you compare the spectrums. Regarding AXF, since we're here to talk about AXF, what you need to really remember is that there are a lot of parameters within the AXF that can be spectrally defined. You can define the diffuse color, of course, the transmittivity, the absorption, the volume diffusion, the anisotropy. We support all of this natively. And I put the emphasis on natively because Thomas Meeker just talked about it earlier. When what most render engines do is that they take the spectral data and they fit to an RGB value. We need to use the spectral value at its core because we want to be able to achieve these type of results. Here you have a car that you have in the daylight, so you have the materials that in fact Gero mentioned on the first day. And when you look at them in a different environment at night with the different illumination, you might see these kind of effects. These are in fact the same materials as before. It's just the illumination that changed. And here you can simulate the different illumination, the different spectrums using a Predict Engine. And I really put the emphasis here on the fact that those materials are AXF. The information comes from the measurements, and we didn't do anything to modify those measures. Of course, we talked about car paint. There's a challenge in representing car paint flakes and so on. All of those parameters are also contained spectrally in the AXF. So these are the things that we also support. Volumetric materials. You mentioned, Mike, that it's a challenge where, since we're integrated in Unreal Engine, this is something that you'll be able to do also within those platforms using AXF. Other types of images, because there are all other values that you can retrieve from other measurement devices, other pipelines that are a bit less accessible than AXF, but here for Pink Floyd fans, I guess you see that this is only achievable if you have a spectral render. You can, of course, do the analysis once again using Predict Lab, and you can achieve those types of results that can be really tricky. And this allows me to continue on the speed of the rendering, because of course you want to be able to do those rendering, but you want to be able to do them fast. And in this way, we have a product that is really simplified since we are integrated in the platform. So for Unreal, the benefit of using Unreal Engine or using Unity is that you have some CAD importer that work really well with different type of inputs from different 3D platforms, Datasmith and Pixies. And for other types of measurements, you have Predict Matter to deal with the different inputs. You put all of this in the rendering, and either you use it in a post-process pipeline for designers, or you can do the raw and optical analysis using Predict Lab. But just to show you the main idea here is that we want to continue to be able to use those rendering and to have them interactive. So we mentioned yesterday the noise and the convergence. Here we want to have all of the spectral information rendered quite fast. So this is quite a challenge. We also, of course, worked also on some denoising technology, working with universities and some PhDs to achieve those types of results. And in fact, this is how we can achieve quite fast rendering on a single GPU. Those results have been generated on a single GPU, so we have the result that can be used for engineering that require less time and less iteration. But you also have the communication renders that you might want to use, where you might want to let the convergence go a bit further. And of course, what we get often, we often get the question, how long does it take to get your rendering? And it always depends on the complexity of the scene. It depends on whether you have the LED at the end of a light guide and a very complex scene, or if the LED is very close to the final layer. But covering different use cases, you have, of course, different rendering times. But you can always cut those rendering time because we made sure that we were scalable on either distant clusters or on-premise clusters. We made a lot of testing with a lot of different GPU providers to really have this scalable approach regarding multi-GPU rendering. So I guess that's it. I went really fast on the presentation because I wanted to let some questions in the end. So if you have any questions, me and my colleagues will be, of course, during the lunch demonstrating what the product does, the different features of the product on our laptops. We have some demo running. So hopefully, if you have some questions, please come and ask us and we'll gladly answer.